then I'm going to share my screen. Okay, so I'm going to go ahead and start today's webinar. So hello everyone, my name is Kai Schwinnicke, and I'm a grad student in the UN Zhao group at UC San Diego. And today I'll be hosting the webinar. Before I introduce our guest speaker, I'd like to remind you that we have a Facebook page called Polariton Chemistry Online Community, where we post updates about the webinar series. We also mean this to serve as a forum for a scientific discussion between people in the community. So please feel free to post any papers or articles that you find interesting, or if you have any comments from or questions from the webinar, please feel free to post them here as well. We also have a YouTube channel called Polariton Chemistry Webinars, where we post recordings of every meeting that we have. Here you can rewatch your favorite presentations, or you can catch up on a talk that you were unable to attend. Finally, I want, as a reminder for attendee participation, you may use the raise hand option. When you click the raise hand icon, I will be notified. I will then notify the speaker, and then I will unmute your mic so you can ask your question. You can also use the Q&A option, where you can type up your questions, and then at the end of the webinar, or at the end of the presentation, we will then address the Q&A submitted questions. Due to the time constraints, if we do run out of time such that we cannot answer all the Q&A questions, I will collect those unanswered questions and then email them to the speaker, who can then answer them on their own time. And with that, we are honored to have Professor Giebink from Penn State University as our featured speaker. Professor Giebink received his PhD from Princeton University, working on organic LEDs and lasers. He was the George Wells Beadle postdoctoral fellow at Argonne National Laboratory, where his work focused on solar energy. He holds 9 patents and received multiple awards, such as the DARPA Young Faculty Award and the NSF Career Award. His current work focuses on studying electronic and optical systems to realize novel and useful devices. Today, he'll be sharing his work on charged Polaritons with us. As I hand over the screen to Professor Chris Giebink, please give a warm welcome from wherever you are joining us today.
Great, thanks, Kai. Hopefully, I hope you can still hear me okay. Let me go ahead and share my screen and we'll get started. Okay. All right, so as I said, thanks again for the opportunity to speak in this webinar series. The focus today is on charged polaritons, which is something that we got interested in when in sort of a broader interest, thinking about doing organic photonics with charged molecules instead of neutral molecules. So starting off with something that I think most of us are familiar with, the excitonic transition for neutral molecules. It's associated with promoting an electron from the HOMO level up to the LUMO level. But what we've become interested in is starting to exploit the optical transitions of charged molecules. So, for example, if I remove one of the electrons from the HOMO, which is the same thing as putting a hole on it in the solid state, I replace that neutral exciton transition with 2 new ones. I can either excite an electron from a lower lying molecular orbital up into that now partially vacant HOMO, or the remaining electron up into what used to be the LUMO. If I remove the second electron and I completely vacate the HOMO, now I've still got transitions from lower lying molecular orbitals up, and this is now the transitions associated with the dication. A good example of these different transitions comes from the classic molecule TPD. It's a diamine molecule. It's very commonly used in organic LEDs for hole transport. And its excitonic absorption is in the blue and the UV. You can see the absorption spectrum of this molecule in solution is the black line here. As a result, it's clear in solution, but if you oxidize it at its first oxidation wave at about 0.5 volt for an hour, that solution turns orange, and that's because of the appearance of 2 new absorption bands, one in the blue here and one out in the near infrared, and those are the 2 transitions associated with the cation that I pointed to on the previous slide. If you then increase the potential in your electrochemical cell up to the second oxidation wave, so this is now at about 1 volt, that solution will undergo another color change and become green, and that reflects the addition of this new absorption band here in the red, which is associated with the dication. So I'll point out that both the cation and dication transitions have very strong oscillator strength, comparable to the neutral exciton transition. And you can also produce them in the solid state. So if you take this TPD molecule and you dope it with a strong electron acceptor like moly oxide, you can see the same transitions, both the cation in the blue and the near infrared, as well as the doubly charged transition out in the red. Except in this case, because we're in the solid state, we tend to refer to them as Polaron and bipolaron transitions. Now, what's relevant for this particular audience is strong coupling. And so the question that we asked early on was, if we think about strong coupling some optical resonance to the neutral exciton transition, we ought to be able to do that with one of these charge transitions. So for example, the cation transition we can couple to the same optical resonance. And in principle, this is a little bit interesting because as compared to our exciton that has both no charge and no spin, assuming it's a singlet, the Polaron certainly carries a charge and is also paramagnetic. And so it opens up maybe some new opportunities. I've given kind of an incomplete list here at the bottom. One in electro-optics, because polarons obviously have a charge, it's thought that you can accelerate polaritons, charged polaritons, with electric field. You can also gate the number of charges and therefore their coupling strength of the cavity. We're also very curious about the possibility for larger Polariton-Polariton interaction strength between charged polaritons and the resultant nonlinearities that might come along with those. Because your Polaron has a net spin, you open up opportunities for manipulating things with magnetic field. This is probably most interesting in the domain of quantum optics. And then the last one that will actually be the focus of this talk is in Polariton chemistry. We've looked at these charged polaritons as a platform to explore charge transfer modifications that occur in the strong coupling regime. So charged polaritons are not particularly new. I think the first demonstration that I've seen is back in the late 90s, early 2000s, where people were looking at strong coupling with trion excitations in gallium arsenide quantum wells, as well as cadmium telluride. There, the binding energy of the trion, so this is a 3-particle complex, typically 2 holes and 1 electron, or vice versa. And the binding energy in these cases is very small. It's about a millielectron volt, which means that you need to conduct all of your experiments at very low temperature. But in different systems, you've got trions with much larger binding energy. So 2D materials, transition metal dichalcogenides, will have binding energies for your trion on the order of 30 MeV. So you can start thinking about doing these experiments at room temperature. And it's even bigger in carbon nanotubes. You've got binding energies on the order of 200 MeV. So this is easy to see at room temperature. And in all these cases, the coupling strength depends on the density of charges, not only on the square root of the charge density. And there's this expectation that you can accelerate these charged polaritons with electric fields. And potentially a very interesting particle that results because of the very low effective mass of the polariton. You get something with a very large charge to mass ratio, which is kind of interesting from a fundamental physics standpoint. In the case of molecules, we're going to couple to these Polaron transitions in solid state. And the molecule that I'm going to focus on is, again, a classic one from organic LEDs. This TAPC molecule is another common hole transport material. And if we look at it oxidized in solution, we see these very strong absorption bands out in the red, peaking at about 1.8 eV, as well as one in the UV that are different from the neutral molecule. The ones in the red are associated with excitation of electrons from lower lying molecular orbitals up into the partially vacant HOMO of the cation. And then this upper energy one in the UV is associated with the excitation of this remaining electron up into higher orbitals. And as I said before, you can create these polarons in the solid state by doping your TAPC with a strong electron acceptor like moly oxide. It's got this very high electron affinity, so we can essentially rip an electron out of the HOMO of TAPC, leaving behind a hole. And the transitions in the purple arrow here are equivalent to the excitation of a hole downwards. So here, for example, is the ellipsometry of TAPC films with differing concentrations of moly oxide. And you can see that as we increase the concentration of moly oxide, the strength of the absorption for this TAPC cation grows. So based on the oscillator strength, or the absorption cross-section that we calculate from the molar absorption coefficient, you can extract some typical numbers. So in a 30 weight% moly oxide film, you've got an absorption at the peak of your Polaron transition of about 5 × 10⁴ per centimeter. And that's associated with a Polaron concentration, the number of ionized TAPC molecules, about 10 to the 20th per cubic centimeter. So very, very high charge densities. So that's what it looks like in thin film. In a microcavity, so in this case, we're just going to construct a simple metal-metal Fabry-Perot microcavity, a thick bottom mirror, and a semi-transparent top silver mirror. 170 nanometers roughly of moly oxide doped TAPC in the middle. And you can see that the the strength of the absorption is sufficient to start to put this into the strong coupling regime. So for a 10 weight % moly oxide film, you start to see the onset of the anti-crossing and the dispersion as we measure reflectivity as a function of angle, increasing, going up. And then if we increase the concentration of the moly oxide, we still see both of those polariton branches, but the splitting between them has increased, as we expect from the increasing the absorbance. In both cases, you get dispersion relations that are pretty well modeled with just a simple coupled oscillator, Hamiltonian. And the magnitude of the Rabi splitting scales roughly with the square root of the absorbance as we vary the concentration of the moly oxide. So at this stage, it's pretty good evidence that we have observed strong coupling, at least in reflectivity. But it turns out that you can also see emission from these charged molecules, which is a little bit surprising because charged molecules, when you excite them, typically have very fast non-radiative decay rates. And so seeing luminescence from them is fairly unusual. But we can see it here. It's certainly very weak. Here you're looking at the photoluminescence of TAPC. The neutral TAPC is here in the green. Most of its luminescence is in the blue with this long tail. And then when you dope it with moly oxide, it strongly quenches the excitonic photoluminescence. In fact, it blue shifts it slightly. So the blue curve here is a factor of 100 lower than the green curve. But you also emerge with this lower energy emission out in the red. And if you blow that up here in the inset, relative to the Polaron absorption band shown in the black, the photoluminescence that we see there in the red is shown here peaking with a slight Stokes shift. It doesn't depend on the excitation wavelength. So the blue curve here is excited in the UV, and the orange and the red are excited at 633 and 640 nanometers. But what's interesting is that you can see these sharp spikes for the red and the orange curve. Those are actually Raman lines. The shift is associated with the change in the excitation wavelength between 633 and 640 nanometers. So it gives you a sense of how weak this photoluminescence is. In fact, we estimate its emission quantum yield at about 10 to the minus 4. It gets a little bit better as you go to lower moly oxide doping concentration. Another important thing to point out is that there's a significant difference in its long-term stability. If you excite the Polaron transition directly in the red at 640 nanometers, the photoluminescence is stable over a long time in air. However, if you excite in the UV, which is exciting a mixture of the neutral molecule as well as that higher energy Polaron excitation, the one that goes up towards what used to be the LUMO, you see this very quick degradation and drop in the PL intensity that's irreversible. So we're certainly degrading the molecules in this case. Now in a cavity, we can also see the photoluminescence. If we take similar film and again put it in a metal-metal microcavity, we see the emergence of the Polariton modes in reflectivity in terms of their anti-crossing, and we also see the photoluminescence follow the same dispersion. In this case, the photoluminescence is on a normalized scale, so I'm not implying that the upper branch luminescence is as intense as that in the lower branch. But nonetheless, it follows the same basic dispersion. So at this point, we're now confident that we've observed strong coupling in both reflectivity and photoluminescence. And in the cavity, you get a small increase in the relative PL quantum yield compared with the bare film. So this is what the photoluminescence maps look like as a function of angle. Here is the experiment. And for a negatively detuned cavity, most of the emission comes out near k = 0 in the lower branch, which is, I think, nominally expected. When you positively detune the cavity, so you shift the cavity mode up above the bare Polaron energy, you still see the peak of the emission at near k = 0 in the lower branch, but you also see an increasing amount of emission up along the upper branch. It's actually displaced slightly above it. And we're able to explain this, at least qualitatively, just with a simple dipole emission transformation matrix calculation. So this is just the usual transfer matrix calculation with, for dipole emission. And just looking at the distribution of emission anyway, we see qualitative agreement. We also see a reasonable qualitative agreement, I would argue, in the relative change in the PL quantum yield between what the transfer matrix model predicts and experiment. And so what this suggests is that, at least from a very simple standpoint, we can explain the population of the Polariton modes just from radiative pumping. We're essentially just fluorescing from the exciton reservoir, or rather the Polaron reservoir, into the Polariton modes, as well as any residual emission from the tail of the neutral TAPC pumping the upper branch as well. It may be more complicated than that. All I'm saying at this point is that it's sufficient to just invoke fluorescence into the Polariton modes to explain what we see coming out of the Polaritons. Okay, so that's just kind of an introduction that says that we can observe strong coupling with these Polaron states, both in reflectivity as well as photoluminescence. But because they're charged, there's also kind of this interesting possibility of looking at them in terms of photoconductivity as well. And that's what I'm going to focus on going forward. And got motivated by wanting to understand cavity effects on charge transfer. And so a couple of years back, Felipe Herrera and Frank Spano published a very interesting paper which explored modifications in photoinduced electron transfer that might come about from strong coupling. And at a simple level, you can understand it as essentially two basic effects. If we look at sort of an energy generalized coordinate diagram for the electron transfer process for a weakly coupled donor acceptor pair, it might be exciting from the singlet ground state up into the first singlet excited state, relax, and then undergo charge transfer into the charge transfer state, where we've got to overcome the reorganization energy. And there's a certain driving force between the singlet state and the charge transfer state. In the strong coupling regime, there's two things that change. One, the driving force changes because of the energy splitting from the bare excitation to the upper and the lower polariton. But at the same time, you can also enter what's known as the Polaron decoupling regime, which effectively changes the reorganization energy. In this regime, instead of undergoing this nuclear reorganization, going into the first excited state, the Polaritons essentially inherit the nuclear configuration of the ground state. You can look at this from a couple different perspectives. At some level, the fact that you've delocalized a single excitation over a lot of different molecules means that you're essentially inheriting most of the ground state from all these different molecules. But from just sort of a classical phenomenological picture, you can also look at it from a dynamic standpoint. When you've got a very high Rabi flapping rate, the excitation is essentially transferring on and off molecules faster than their nuclei can actually reorganize. And so during the time span that the excitation is on there, you're essentially frozen in the nuclear ground state configuration. In any case, so both of these configurations, or both of these parameters, enter very strongly in a Marcus type description for charge transfer. And so the basic conclusion was that you can have a very strong impact and non-trivial impact on photoinduced electron transfer by strong coupling. So we looked at this and thought that there was a good reason why charged polaritons might be useful, because if we just look at the current that we measure in a thin film, it's essentially the product of a bunch of electron transfer reactions. So in the dark, for example, if we've got a hole and it's moving to the right, that's just the product of a bunch of electron transfer reactions in the HOMO to the left. Photoconduction, if, for example, we excite a hole downwards, then it potentially undergoes electron transfer in its excited state before it relaxes back up into the HOMO. And so we get to probe the electron transfer events that happen in this excited state, this lower lying molecular orbital. And so the thought was that, well, Polaron photocurrent directly probes photoinduced electron transfer, and we can measure current very sensitively. So maybe this is a good opportunity to use this in order to explore changes in electron transfer that happen in a microcavity. So we started off with a control sample, which is nominally a half cavity. So we start off with an ITO electrode on the bottom, 170 nanometers of moly oxide TAPC, and a semi-transparent silver contact. And then we're going to bias this, and we're going to measure the photocurrent synchronously that we detect from chopping monochromatic light. We're going to measure the photocurrent action spectrum, essentially. That's the external quantum efficiency that we measure for our photocurrent. And when we do that, for this bare film, we see our photocurrent action spectrum that more or less mimics and follows the absorption spectrum of the bare polaron. So here's the main transition, and here's the shoulder. And we see both of those features in the photocurrent superimposed on sort of this tail, this exponential decay that we attribute to the neutral TAPC tail, just exciting neutral molecules and undergoing traditional exciton dissociation. But the thing that I'll point out is that the line shape, maybe not surprisingly, is independent of the bias. So the magnitude, of course, goes up a lot when we increase the bias and we extract the charge more efficiently, but the line shape doesn't change. The reason that I emphasize that is because that's not what happens in a microcavity. So I'll get to that in a moment, but it's maybe not obvious what the photoconductivity is associated with when you excite a polaron to begin with. With excitons, we're typically exciting an exciton. We undergo exciton dissociation. We get an electron in hole, and that gives rise to photoconductivity. In this case, we actually look at it in close analogy to what happens in inorganic photoconductors. So this is things like mercury-doped germanium. There, you've got these mercury acceptor levels, which may have a hole that you can excite, in this case in the infrared, out into the valence band. It will drift for a certain distance before it ends up getting retrapped on another acceptor. And the distance that it travels essentially gives you your photocurrent. In our case, the acceptor levels are actually the moly oxide counterion. So remember, we transferred an electron onto the moly oxide, and the residual hole is still strongly bound coulomically. The binding energy is hundreds of milli-electron volts. And so what we really created is a bunch of charge transfer complexes in their ground state. And so what we envision is when we come in and we excite with a photon one of these holes, this is looking at it in energy space. It goes down to one of the lower lying molecular orbitals and has a higher probability of being able to hop to maybe one molecule, maybe one more, before it relaxes back to the HOMO. So in real space, we're now up to this molecule. And so this kind of looks like the thermalization distance in an Onsager type dissociation model. And then depending on temperature and electric field, that'll determine the probability that this hole fully dissociates and goes off to hop on and contribute to photocurrent, or maybe it gets pulled back and rebound into this charge transfer complex. So it's an Onsager-like model, and it's really charges getting kicked away from their counterions by photon absorption. Now, the decay rate of these photoexcitations is very fast. So this is the transient absorption spectrum measured by Natalie Banerjee's group. And what you see here, this is the bleach of the Polaron after coming through and pumping it directly. And you can see that that actually decays very fast, within about a picosecond or so. So most realistically, we're only going to be able to hop maybe one molecule, maximum two, before we relax back to the HOMO. But what's left in this transient absorption spectrum at long times, so nanoseconds and longer, is a first derivative line shape relative to the Polaron absorption, which is very reminiscent of what you expect for electroabsorption. And this kind of makes sense in this picture. When we come in with a photon and we kick off the hole, we've disturbed the equilibrium electrostatic field distribution. And so we set up electroabsorption of nearby cations. And so we see this electroabsorption spectrum persist over much longer time scales, nanoseconds and even longer, until the charge carrier distribution returns to what it is in equilibrium. So this is the picture for photocurrent in a bare film. When we go to a microcavity, so this is now now the same basic structure. What we've done is we kept the same moly oxide TAPC film, the same semi-transparent silver mirror, and replaced the ITO with 100 nanometers of aluminum. We confirm that we've got strong coupling in reflectivity. So in this case, we've got I think it was a 38% moly oxide film. And the dispersion in this case, we've got our cavity mode that is close to zero detuning at K equals 0. And looking at the photocurrent now, it is very confusing at first glance, because now we're looking at the photocurrent action spectrum as we vary the bias, so plus minus 0.7 volts going down to plus minus 0.1. And in the higher bias spectra, you can see what is kind of reminiscent of the Polariton peaks here and here. But we see that the shape of the action spectrum changes dramatically. In addition to the magnitude, which we expected, at very low biases, we no longer see the Polariton peaks. We see kind of a single peak that's actually sighted right around the peak of the uncoupled Polaron absorption. That's not weird enough. The phase of the photocurrent, so this is the phase relative to the chopper that we're using at 400 hertz, also undergoes dramatic variation spectrally. So the phase of the photocurrent when you excite at, for example, red light is different than when you excite with green light, for example. This is also very unusual because all the dynamics that are happening with these Polarons are picosecond, nanosecond timescale, and yet we're seeing effects on a millisecond phase timescale for our 400 hertz chopping. So this was very puzzling in the beginning, and what we realized was that the photocurrent that we're observing has two components. So there is the drift in response to the electric field, but of course there's also a diffusion contribution that we hadn't originally thought about. And that's just because we've got a gradient in the optical field intensity profile in the cavity that leads to diffusion of these excited Polarons. And so if we look at the sum, the phasor sum of the drift and the diffusion photocurrent contributions, the drift, of course, changes sign as we change the bias. There is no built-in field in these cavities. Their current voltage characteristics are symmetric. But the diffusion is governed by the intensity gradient in the cavity, so that's field independent. And so the measured signal is the sum of these. And if we take the measured signal for positive bias and the measured signal for negative bias, and we add them together, that cancels out the drift contribution and gives us twice the diffusion. And if we subtract one from the other, that cancels out the diffusion and gives us twice the drift. And so we've got a way of isolating the drift and the diffusion contributions to the photocurrent by adding and subtracting the photocurrent spectra at a given positive and negative bias. And so this is what those two contributions look like. The drift contribution, now we see the Polaritons, or at least what looks like Polariton peaks being present at all biases, but most importantly, it collapses that phase to a constant, which is really what you have to expect. It does the same for the diffusion. Phase for the diffusion now becomes constant and spectrally invariant. And the magnitude of the diffusion is largely independent of bias. In principle, it should be completely independent of bias. And to a large extent it is. This 0.7 volt spectrum starts to inherit some error from some drift that overlaps with it. But nonetheless, it helps rationalize these spectra and make things a little bit more intelligible. But one thing that I'll point out is that the Polariton peaks in the drift current here become less pronounced at high bias. So you can very clearly see this peak and this shoulder at low bias, but it becomes less clear that they're there as you get to higher bias. And this is unusual because it's, as I said, very different than what you see in the bare film, where the line shape remains constant and independent of the bias. If you look at those spectra on a linear scale now, so here is the photocurrent spectrum from the lowest bias, 0.2 volts, and then the one for the highest bias at 4 volts. We can explain the difference between these by an additional contribution from a component that peaks at the bare excitation. So the lower Polariton and the upper Polaritons give you the peaks that we see in the low bias spectrum. And if we keep those constant, but we add in a contribution at the uncoupled excitation, we can reproduce what we see at higher bias. Now, it turns out that this changes depending on the angle that you excite your cavity. So if you excite at normal incidence, for example, which is very close to zero detuning, you see this. But as you go towards higher angle, so this is now going to positive detuning of the cavity mode. Now, in this case, we don't see any contribution from the uncoupled excitation. We're able to explain the photocurrent spectra solely with the lower and the upper Polariton contributions. Now, it's important to emphasize that there is no change in reflectivity of these cavities with bias. So the reflectivity is totally independent of bias, but yet the line shape of the photocurrent is changing, which is very unusual. And what it suggests is that the photocurrent from weakly coupled excitations has a stronger bias dependence or dependence on electric field than the case of strongly coupled excitations. And so this is really a summary of a bunch of different cavities. Here's the data that we just looked at from the previous slide. So in this case, the 0 degree excitation, that was at 0 detuning. And what I'm plotting here in the blue and the red is the amplitude of the Polariton photocurrent contributions. So the upper and the lower Polariton photocurrents have essentially exactly the same field dependence at 0 detuning, but the uncoupled excitation exhibits a stronger field dependence at low bias. And that changes as you increase the detuning, for example, by increasing the angle for the same cavity, we lose the observation of the uncoupled excitation, and the Polariton peaks start to exhibit a different field dependence at low bias. If we increase the positive detuning even more by growing a thinner cavity, 125 nanometers in this case, we see that the lower Polariton exhibits the stronger field dependence as compared to the upper Polariton. And if we go to negative detuning by growing a thicker cavity, we see that reverse. The upper Polariton has the stronger field dependence as compared to the lower Polariton. So the key takeaways from this are, one, that we can only resolve.
Professor, we have a question from the audience.
Sure.
Ben Liu, go.
Hi. So I have a question about the devices. So how do you make the organic layer? I mean, will be the short circuit an issue for the devices?
Yeah, so that's an important point. So the fabrication of the devices is all by thermal evaporation. So we thermally evaporate the aluminum and then co-evaporate the TAPC together with the moly oxide and then the silver mirror on top. Because they're very highly doped films, you get a lot of photocurrent, or rather just a lot of dark current, period, which is problematic when trying to measure the photocurrent very sensitively. So one thing that we do is we're actually performing all these measurements at low temperature. And in that case, that essentially reduces the amount of these ground state charge transfer complexes that will dissociate and gives you a much more resistive film. So I guess important to note that these measurements that I've been talking about so far, for the photocurrent anyway, are done at low temperature at 77 Kelvin.
I see. Thank you.
And then we have another question from Matthew.
Sure.
Okay, so in some cases, you find that the uncoupled states participate in the photocurrent, but in other cases they don't. So do you think it's more due to the initial distribution of states that are excited, or do you think it's also due to the radiative pumping mechanism, and maybe that plays some role?
So far, we've viewed it just as the initial distribution of states that are excited. We're still trying to understand it in more depth, but that is our first order approximation right now. We haven't looked at redistribution of the excitations along, for example, the different Polariton branches, or going back into the reservoir from a Polariton, for example. Although you'll see when I talk a little bit more about what we think is happening with the charge transfer, it of course does involve uncoupled molecules because we have to undergo charge transfer from a polariton to an uncoupled molecule. So those do get involved at some point.
Thank you.
Okay, so coming back to kind of the key takeaways so far is, one, we can only resolve the uncoupled photocurrent contribution near zero detuning. So that's this curve here. It has a stronger bias dependence than the Polariton modes at low field. And then the other thing is that essentially the most matter-like branch at positive and negative detuning exhibits the strongest field dependence. So at negative detuning, that's the upper Polariton. And at positive detuning, that's the lower Polariton. The exchange in the field dependence here is another key observable. And so we've kind of given this a phenomenological interpretation, again, relying on that Onsager picture of photocurrent in the bare film. So remember, in the bare film, we kick one of these charges with a photon, and that allows it to undergo maybe one or two hopping events out to some distance r naught, which we call the thermalization length in Onsager theory. And then at that point, it's relaxed back to the HOMO. And then there's a probability that depends on the applied field and the temperature that this thing either fully dissociates and goes on to contribute to the photocurrent, or it goes back and gets retrapped with its counterion. And the point here is that depending on R naught, that strongly affects the electric field dependence of the dissociation. So this is the dissociation yield of these initial ion pairs. And when the initial thermalization length is very short, so the starting distance is very close to the counterion, there's a very strong electric field dependence in dissociation. And then kind of intuitively, for something that starts off farther apart, it's much more weakly dependent on the electric field. And so if we view it in this lens, it suggests that the strongly coupled excitations appear to have a larger thermalization length than the uncoupled excitations, at least in this framework. And so our model then is of our, so we've got our photon coupled to our excited polaron, coupling strength G. And then we've got most of these things decaying just with natural decay and dephasing, so the leakage of the cavity photon out, as well as just dephasing of the material excitation. This happens very fast. Our cavities are low Q, so we're talking tens of femtoseconds. Charge transfer is another possible decay pathway for the polariton. If we undergo charge transfer to an uncoupled molecule, that destroys the coherence and destroys the polariton. But charge transfer rates are typically slower, on the order of picoseconds. And so this is probably not a dominant decay pathway. And so if we come in with a photon and resonantly excite our polariton, the vast majority probably just decay and dephase naturally. Those that dephase go into uncoupled excitations, which have a short Onsager thermalization length. So they have a strong field dependence for dissociation. So that gives you one contribution to the photocurrent that we observe. But then a small fraction of the polaritons will undergo, they'll decay by undergoing charge transfer. And for reasons that I'll hopefully try and explain in another slide or two, that gives you a starting pair with a larger Onsager thermalization length. And so it has a weaker field dependence in dissociation. So that's a second contribution to the photocurrent. And if we take this type of model and we just put in some basic numbers. So for example, the field dependence in the Onsager model for the photoconductivity from just uncoupled excitations is the orange line here. And those from strongly coupled excitations is the green line here. Now, as I said, the vast majority of polaritons just decay naturally into uncoupled excitations. And so at high bias, these guys dominate, but the small fraction of those polaritons that do undergo charge transfer and end up with this more weakly field-dependent dissociation, those guys start to dominate at lower bias. And so this type of model, at least qualitatively, explains this branching in the field dependence between the uncoupled excitations and the polariton excitations that we observe at low bias. Now this leaves us with maybe the bigger question, which is how would strong coupling actually modify the thermalization length? And the answer is, well, presumably by accelerating the initial electron transfer event off the initial molecule, so this event right here, because it can't change any of the subsequent events. As soon as it modifies or we undergo charge transfer from a polariton, that destroys the coherence. The polariton's gone. None of these subsequent downstream hopping events can be impacted. We looked, of course, in the context of Felipe and Frank's model, but we don't think that we can explain our data based on that model in this case, because one, we see the upper and the lower polariton behave identically at zero detuning, where you expect a big difference between those in that model. And the other reason is just practical. The Rabi splitting in our particular case is probably too small for significant Polaron decoupling to be happening. And so we looked at maybe just a simpler alternative, which has to do with the disorder in the film. So these little ovals are meant to be the TAPC molecules, and in this type of thin film, we've got a lot of positional and energetic disorder, which means that we've got a lot of different electron transfer coupling strengths between, for example, our excited Polaron and neighboring molecules. Those with farther apart have a lower rate of electron transfer. Those that with particularly favorable orbital overlap might have higher electron transfer rates. In any case, the probability of this charge hopping onto neighboring molecules depends on the total rate of electron transfer to all those different molecules in comparison with the normal non-radiative decay rate. If we look at what happens if we delocalize this excitation in a Polariton type excitation, so now that excitation is shared among many different Polarons, those with the largest coupling strengths, just by virtue of fortuitous orbital overlap, are going to dominate, and you potentially have a pathway to accelerate the overall rate of electron transfer for the Polariton. And so just from a simple back of the envelope calculation, if we look at the electron transfer yield as the competition between the net electron transfer rate off a given excited Polaron over its total decay rate, we average that over an ensemble of different electron transfer rates. So we can make a guess at this just based on Monte Carlo type hopping models that describe the conductivity of organic semiconductors. So for example, it's centered around 10 to the 11 per second with plus minus an order of magnitude or so in breadth. And we compare that to a delocalized excitation where we delocalize over n different molecules. So we essentially get a contribution of 1 over n of their electron transfer rates. And we look at the electron transfer yield as a function of the number of molecules at which we're delocalizing over. You can see that we do predict an increase in the electron transfer yield. So potentially an increase in the electron transfer yield allows us to start off with a larger thermalization length. And as a result, that gives us the difference in the field dependence of the photocurrent. So I'm more or less out of time, so we'll end there and just summarize by saying that I've tried to show you that we can strongly couple to Polaron optical transitions in heavily doped organic semiconductors. We see that both in reflectivity as well as in photoluminescence. And then also in photoconductivity, we see some non-trivial effects in the strong coupling regime. Essentially, the photocurrent from Polaritons depends more weakly on the applied electric field than when you excite uncoupled excitations in the same cavity. And we phenomenologically associate that with increased Onsager thermalization lengths, which I'll note should also manifest for exciton dissociation in a neutral system. So that is another platform to try and explore this, although you want to make sure that the exciton dissociation of the bare molecule is very inefficient. If you do this with a donor acceptor type organic photovoltaic system, it's always efficient. You don't see any of these very small changes in a cavity. And then if you take anything from this, I would hope that it's that there are some interesting opportunities to do organic photonics with charged molecules. You essentially have the same transition properties as neutral excitons, same oscillator strengths, but now you've got some new electric and magnetic degrees of freedom that may be kind of interesting to play around with. So I want to thank the students that actually did this work. Nina did all of the photoconductivity work and figured out that problem. Joyce did the initial reflectivity and photoluminescence experiments, and then Alex and Rachel were important in understanding the basics of some of these charged molecules. Natalie Banerjee and Demetra in her group did the ultra-fast transient absorption, and then our colleagues at Dow, Tony and Sukrit, helped us with some of the DFT calculations to understand the transitions that we were seeing. And then, of course, NSF, DOE, and the Air Force for their funding support, and you for your attention. So thanks very much.
Thank you. We have a couple questions. Go ahead, Joel.
Hi, Chris. Sorry, can you explain again this result at 65 degrees where the photoconductivity is dominated by the Polaritons? Okay, so I mean, presumably also a large majority of the population is going to the dark states. So again, does this happen only at given, well, I mean, based on your data, it happens at a wide range of biases. So can you explain that again? How come the photoconductivity is not being dominated by decay into dark states?
So it is. So the thought is that the vast majority of our excitations essentially decay to dark states. That is essentially this picture right here. So we excite a polariton, and when I say it dephases, it's essentially decaying into dark states, uncoupled excitations in the reservoir, and so that dominates in pretty much all cases. When we go to very photon-like excitations, so out at 60 degrees, positive detuning for the upper branch, there it looks, well, so in this case, the lower branch looks the most matter-like in terms of its field dependence. The upper branch, as far as I can tell, is all we're seeing for the upper branch is those polaritons that do decay by charge transfer, because in addition, so when the polaritons decay into the dark states, we see the photocurrent contribution from them, but the polaritons that decay by charge transfer, which is a small fraction of them, we're going to see those in the photoconductivity as well. So
this is just because the dark states are really essentially overlapping the line shape of the lower polariton at 60 degrees.
That's correct. So so actually you bring up, there's one slide that I cut out for time, but I'll point to it now. So this is what you're looking at is the dispersion of the polaritons in reflectivity and the polaritons in photocurrent. The polaritons that we observe in reflectivity are the circles here, and the different colors are different cavities and different angles. So this is the usual dispersion that we expect, and to a large extent, the polariton peaks that we see in photoconductivity follow this dispersion, but there are two notable differences. One, in the upper polariton at high detuning, we see a red shift in the photoconductivity's peak as we increase the bias. And then two, the photocurrent polariton that we see follows the dispersion at essentially at larger detuning, but then it's not as low in energy as the polariton in reflectivity here. And so this gap, we think, just reflects the overlap between the polariton states and the uncoupled states. So obviously we have to have overlap to undergo charge transfer, and those polariton states that overlap with the uncoupled states here fairly closely gives us the energy of the peak that we see in photocurrent, whereas the polariton states that we see in reflectivity, of course, are at much lower energy. So I think there's something very similar happening here. It has to do with the overlap between the upper polariton and essentially uncoupled states at higher energy that's governing what we're seeing up there. Does that?
Going back to that point, but your model does not just say that the polaritons are an optical filter, right? Like, essentially, the polaritons do have, say, larger Onsager radii.
Correct.
But then, if you were just to assume that they were just optical filters, would you get the same?
Oh, if you assume that the polaritons were just an optical filter, then you would expect that the photoconductivity should follow that filter exactly. So you wouldn't expect to see this deviation here. You would expect the stars to follow exactly. So the fact that we see this deviation implies that there's something else going on. And then, of course, optical filter can't explain the difference in field dependence, since that's kind of independent. Go ahead.
You say the optical filter cannot explain the field dependence, or can?
An optical filter effect cannot explain the field dependence. If it was just an optical filter, then the line shape of the photoconductivity should be independent of the bias.
Thank you very much.
We have another question from Wei.
Chris, just follow up. I found it's very interesting that the image or the photocurrent of the dark mode actually depend on the detuning, which I usually think the dark mode would not depend on detuning. So do you have any thoughts on that?
No, I mean, you're exactly right. I don't think the photocurrent of the dark mode depends at all on the detuning. It is just how much the contribution from the Polariton changes. So the dark modes are any excitations that transfer into the dark state reservoir or have dephased. Those have their own field dependence, and at that point they've lost all memory of how they were created. It's this variation in the contribution from the polaritons that undergo charge transfer that ends up making a difference in the photocurrent field dependence. So normally for the dark excitations, those just have this field dependence shown here in orange. But as we change the detuning, we change the extent to which we're exciting polaritons and their matter fraction, so the extent, the capability that they have to undergo charge transfer. And so as we push this green line up and down, we change what the sum of them, which is what we observe, looks like in the blue. So in a system where we don't excite the polariton, all we see is the orange contribution, whereas when we detune and resonantly excite a polariton, we start to see an increasing contribution of the green, which on this log scale only affects things at low fields. It's still dominated at high fields by the uncoupled excitations.
Right. So I guess so then at the high reflective or excitation angle, that is the 60 degree that you show, there is no the contribution from the dark mode at all. So is that because that the polariton just does not relax to the dark mode, or?
No. Okay, so I think I see where the confusion is going, and I should have emphasized this. Just because we don't see a contribution from the uncoupled state in the fitting doesn't mean that it's not there. In fact, it probably is, and the reason is that our fitting can't resolve the uncoupled excitation from, in this case, the lower branch, because they're basically at the same energy. So it's very likely that there's a contribution from the uncoupled states. It's just that we can't discern it from a fit. We can fit just as well with 2 as we can with 3, so there's no reason for us to include a third peak.
Okay, I see. Thank you. If I can follow up, just one quick question. So overall, do you see a modification of the photocurrent by strong coupling compared to just in the outside the cavity?
We see an increase in the photocurrent at low bias from strong coupling. So relative to what's at high bias, when we excite polariton modes resonantly, we see an increase in photocurrent by a factor of 2, 3, 4, as compared to if we just excited an uncoupled film or the paired excitation in the same cavity. At the highest bias, everything gets dominated just by the uncoupled excitations because they're the majority, and at high enough bias, we dissociate all of those, and so the small number that where the polariton actually makes a difference gets washed out and we never see it, or at least that's the interpretation.
That makes sense. Thank you.
Okay, and then we have a question through the Q&A option from Kamala Kadas. Is it only the anti-crossing between the cavity and polariton you consider as the criteria for calling it a case of strong coupling?
We've used the anti-crossing in both reflectivity and photoluminescence as our criteria, yes.
And then we have another question from the audience. Give me a second here. Go ahead, Claudia. You're muted. Claudia, you're muted. Okay. I guess I'm just gonna, I don't know, maybe that was a misclick on that end. Okay, well, that seems to be all the questions for now. Thanks again, Chris, for an amazing talk. If you could stop sharing your screen so I could close out this meeting.
Yep, let me go ahead and. All right, you should have it back.
All right, thank you. So I just want to introduce the next week's speaker, Professor Agnes Giebink from the University of Debrecen. Once again, join me in thanking Professor Giebink for a wonderful talk, and see you all next week.
Thanks, Scott.
Thank you.